All right, today we're going to talk about a discovery, one that came from a glitch. A tiny, tiny error that most people would have just ignored. But here's the thing about physics. Sometimes those tiny glitches, they can rip open whole new layers of reality. So let's get into the story of the Lamb shift.
Let me ask you something, and it's going to sound a little philosophical at first. Are two things that are supposed to be identical ever really the same? I mean, truly? It sounds like a late-night dorm room question, right? But believe it or not, back in the mid-20th century, physicists were grappling with this exact puzzle, but with the hydrogen atom. And the answer they found? Well, it completely changed how we see the universe. All right, first up, this tiny cosmic glitch. See, at the time, the reigning champion of atomic theory was something called the Dirac equation. I mean, this thing was a masterpiece. It was elegant, it was powerful, and it was ridiculously accurate. Almost. There was just one tiny, nagging problem. And here's the problem in a nutshell. On one side, you've got the theory, the beautiful Dirac equation. It predicted that these two specific energy levels in a hydrogen atom, we call them 2s and 2p, should have the exact same energy. No difference, identical twins. But then, there's the real world, and reality wasn't playing by the rules. Every time they measured it, the 2s state had just a smidge more energy than the 2p state. A tiny but very real difference. Now, you might be thinking, so what? It's a tiny difference. But this was way more than a rounding error. This little discrepancy, which we now call the Lamb shift, was like a tiny crack in the foundation of everything they thought they knew about atoms. Figuring it out became a top priority. Why? Because whatever was causing this shift, it was something completely new, something totally missing from their best theories. So where do you even start looking for an answer? Well, physicists turned to a really, really weird and counterintuitive theory called quantum electrodynamics, or QED for short. And QED suggested something crazy. Maybe the problem wasn't the atom. Maybe the problem was the empty space around the atom. Okay, hang on, because this is where things get wild. The central idea of QED is that a vacuum, empty space, isn't empty at all. Not even close. It's actually this seething, bubbling foam of virtual particles that are constantly popping into existence and then vanishing again. It's chaos. And if you're an electron living in an atom, you're not just sitting there peacefully. You're constantly being bumped and jostled by this quantum foam. You jitter. And that jitter, QED predicted, was just enough to nudge its energy level. And here's the really crucial part. QED wasn't just some weird story. It made a real, testable prediction. It actually put a number on it. The theory calculated that this tiny energy difference between the 2s and 2p states should correspond to a very specific frequency, a frequency you'd find in the microwave part of the spectrum. That was the clue. It was like a treasure map leading to a very specific radio station. Okay, so you have a prediction. Now how in the world do you measure it? This is where physicists Willis Lamb and Robert Rutherford come in with a truly brilliant experiment. Honestly, you can think of it like a ghost hunting machine. They weren't looking for ghosts, of course, but for the invisible effects of this quantum vacuum on hydrogen atoms. The core idea behind their machine was, when you break it down, incredibly clever and pretty straightforward. Step 1, you create a nice controlled beam of hydrogen atoms. Step 2, you zap that beam with microwaves. And step 3, you watch very, very closely for a tiny flash of light that tells you you've hit the jackpot. But the devil is in the details, and the actual setup was just wow, so clever. They'd start with a hydrogen source to get the atoms all energized. Then they'd funnel those atoms into a super narrow beam. They'd shoot this beam through a box where a microwave generator would hit it with just the right energy. And at the very end, a detector was sitting there waiting, ready to catch any tiny flash of light coming off the atoms. But the real trick, the secret weapon of this whole experiment, comes down to a quirk of these two energy states. See, the 2s state is what we call metastable. It hangs around for a while, about a tenth of a second, which in the atomic world is an eternity. The 2p state, on the other hand, poof, it decays almost instantly. This difference was everything. It gave them just enough time to get those 2s atoms into their beam and zap them with microwaves before they disappeared. So, okay, the machine is built. The secret weapon is ready. The stage is set. All they had to do now was hunt for that one single magic frequency that QED said should exist. And this was it, the moment of truth. The team started carefully, slowly tuning the frequency of the microwaves.
It's just like turning the dial on an old radio, right? Just sifting through all the static, listening for that one clear station. They were looking for a spike on their detector, a sign that the microwaves were hitting just the right note, kicking those 2s atoms up to the 2p state, which would then immediately flash.
And then, bam, they found it. Right at 1057 megahertz, the detector went crazy. This was it, the smoking gun. The exact frequency that matched the energy gap. It was like they had finally heard the whisper from the quantum vacuum.
And you can see exactly what that discovery looked like. When the microwaves were on the wrong frequency, nothing. Just a little bit of background noise. But the second they dialed it in to 1057 megahertz, the signal just explodes. That huge spike is the flood of light from all those atoms being kicked up to the 2p state and decaying. It was undeniable. The theory was right. So what's the big deal about one number? What did this experiment really mean? Well, its impact, it was nothing short of a revolution. It basically delivered a new verdict on how reality actually works. So let's talk legacy. This one measurement was the knockout punch. It was the first solid proof that QED was right, that the vacuum is not empty. It showed us that the old Dirac theory, as great as it was incomplete. It forced us to accept a much, much stranger quantum reality. And beyond that, it basically invented the entire field of high-precision physics, allowing us to measure the fundamental constants of our universe with incredible accuracy. And all of that came from one tiny little glitch. And that really brings us to the final mind-bending thought here. The Lamb shift proved that even the most empty part of the universe is actually buzzing with activity. It just makes you wonder, right? If a perfect vacuum is hiding secrets this big, what else is out there? What other fundamental truths are just hiding beneath the surface, waiting for us to ask the right question and build the right machine to find them?